Hi, in this video we are going to test our binary search tree remove operation, but sorry for that, I have made a few mistakes. First of all, we have specified that self.left node. Of course, the self doesn't have any left node, it is the node.left node that we have to check. Here again we have to check the node.right child. Here I made a mistake because the self instead of elf, I think I typed something like elf or something like this. We have to define the self.getPredecessor. And it's very important that at the end we have to return with the node. I usually forget about this return. Anyways, we have to do it. It's very important. So that's all about the update. Sorry for that. And for example, I'm going to insert some numbers. I think it's a bit more straightforward at what's going to happen. 5 and for example 1. If we would like to get rid of binary search tree.remove, for example 5, then we are going to remove an item with a single left child. So basically, with a single left child, it's going to be printed out. Let's see whether it's working fine or not. As you can see, we have managed to get rid of 5 and 1, 10 and 13 is going to be the numerical ordering, and removing a node with a single left child. Let's remove a node with a single right child. I'm going to insert, for example, 14, and if we remove 13, it's going to be this situation. Removing a node with a single right child, it's going to work just fine. What if we would like to get rid of the root node? It's going to get rid of 10, and the 10 has a left child 5, and the 5 is going to be the predecessor. So the 5 is going to be swapped with the root node, and then this 10 is going to be a leaf node, so it's going to be printed out. So let's see whether it's working fine. Removing a node with 2 children, then removing a leaf node, and it's going to yield the right results. So it is working fine. That's all about binary search tree. We have been discussing the insertion operation, how to make the in-order traversal, how to get the maximum item, how to get the minimum item, and at last how to remove a node from a binary search tree. But it's very important that, okay, it's working fine. But the problem with binary search tree that it can get unbalanced, and if it's unbalanced, then this logarithmic time complexity is not going to be valid. Because if it is a balanced tree, then the remove node operation will have the logarithmic time complexity, the get mean value operation is going to have the logarithmic time complexity, then the get maximum method is going to have the logarithmic time complexity. Of course, the in-order traversal is going to have the linear time complexity because we have to iterate through all the nodes. So we have to consider every node on a one-by-one basis is not going to be better than ordo n, but this is how it works, so it's not a problem. If we would like to consider every item, of course it's going to take ordo n linear time complexity. So we just have to make sure that the tree is balanced, and this is why more advanced data structures such as AVA trees and red-black trees came to be. So this is what we are going to discuss in the coming sections. Thanks for watching.